Hi everyone. Today our group project is going to talk about boiling heat transfer, which is from the article named Application of Nano Refrigerants for Boiling Heat Transfer Enhancement, employing an experimental study which is published in 2019. So in our project, we're going to separate into 4 parts, which is first one is about what is about our project. Second one is the method. The third one is going to be the graph and formula, and the last one is going to be the results and the conclusion of this project.
Start with the introduction. Question: why should we need to improve heat transfer rate in boiling heat transfer technology? So, boiling heat transfer technology has been applied in various major scientific fields such as chemical engineering, aerospace, refrigeration, and power generations. Therefore, I will raise you some example, raising 2 examples from the power generations field. So this is our for example of the implication of a boiling heat transfer technology in power generations, which is about nuclear power plants. And what we have here is a diagram of nuclear power plant and nuclear power plant. So heat in nuclear power plant, heat is produced by it's produced from nuclear chain reactions in the control rod, and that heat will be transferred to steam generator in order to boil the water in that steam generator to create steam, and those steam will be used to move the turbine in order to produce electricity, as you can see, through the electric generator, and the process will be in cycle. And however, what we should focus here is in the red in this red circle. How do we transfer heat that produced from a nuclear chain reaction to a steam generator? To do that, we use a pipe. To use that, we use refrigerant, and those refrigerant will be transferred through pipe like this, as you can see. So this is boiling. This is boiling heat transfer technology applications by boil the water boil the water in the control rod and transfer that water to a steam generator in order to create steams. And for the second example, we use the coal power plant, the application of boiling heat transfer technology in power generations. As you can see here, in coal power plant, heat is produced by burning the coal and to produce heat. And those heat will be used to boil the water inside this pipe, as you can see here, inside this pipe, in order to produce steam, and those steam we are used to move the turbine just like in nuclear power plant in order to produce electricity through electric generator here, and the cycle and the things will happen in cycle like this, as you can see in the diagram. Therefore, this is another application of boiling heat transfer technology. Therefore, it is important that we could find something. To increase the transfer rates between the boiling parts to the refrigerants in order to increase the heat efficiency and decrease the heat loss during the transfer rate from the boiler to the refrigerant.
So I'm going to talk about the components or experiment. So it consists of reservoir tank, pump, flow mirror, heater, test evaporator, condenser. Reservoir tank is a device that stores the liquid that transfers from condenser, and pump is a device that delivers fluid by suctioning it, and flow mirror Flowmeter is the device that measures the flow rate. And for heater, is a device that imparts heat or holds something to be heated. And test evaporator is a device used in process to turn the liquid from a chemical substance. And condenser is a heat exchanger used to condense a gaseous substance into a liquid through cooling. So I'm going to talk about the how experiment work. So for the receiver that stores the water from the condenser and transfer it to the pump where it circulate the fluid and transfer it to a flow meter where it measures a flow rate, and then it goes through the heater where it heated the liquid and transfer it to the test evaporator that turn the liquid from a chemical substance, and then the condenser where the substance change into the liquid state. And for the other accessories that are placed in both heater and test evaporator, they are thermocouple and pressure gauge. It's used to measure the temperature and pressure respectively, and the device that used under the test evaporator is called a transducer sensor. It's used to measure the pressure drop. And in test evaporator, we use various types of test tube. They consist of 4 types with different altitude height. Like my friend Bob mentioned that we use the Flanton tube to enhance the heat transfer rate. And in this, I'm going to talk about 3 methods of heat transfer improvement. We are using a flattened tube, a refrigerant 300A made with polyester oil, lubricant, and copper oxide nanoparticle. For flattened tube, from the experiment, we choosing flattened tube over the circle tube due to it have improve the heat transfer. And for this case, we consider the study or refrigerant 600A that made with polyester oil by 1% mass concentration that proved that it caused least greenhouse gases, and it also saved the cost. Due to my friend have mentioned that when we use 100% of refrigerant 600A, it costs a lot. So that's why we make it with polyester oil lubricant. And for copper oxide, as a nanoparticle that blend with oil, can be stay stable in the experiment for 12 hours. So therefore, it's for every experiment, it can be not run exceed 8 hours. And the reason that we choose copper oxide due to its high thermal conductivity and it made from a condensation which was commonly used in the research. So the reason of adding nano-refrigerant. Actually, nano-refrigerant is the 3 method that I have mentioned in the previous one. So reason I think nano-refrigerant, they are increasing surface area like I have said that we choose the flattened tube. And for intensify interaction between fluid and particle, is improve the interaction between, like I have talked about the copper that blend with oil. So the purpose of using it is to improve the reaction. That's why it can stay stable until 12 hours, and the intensity of fluid turbulence mixing and the more uniform fluid temperature distribution. So in data reduction, for data reduction, the purpose in data reduction is they use to obtain and calculate for the data that they get from the experiment, and their nominal local mass fraction as well defined as the formula here, and the local of matter and the measure of enthalpy and the vapor quality and the conduction in cylindrical coordinate system through the thickness of the two balls. So that's all of the data reduction. So that it's just the formula that the, they, they use to calculate the data they get from the experiment. That's all. Oh, so for this one, it's just a graph that is a comparison of the obtained result of heat transfer coefficient with the predicted by the author for the flow boiling inside part. It's just a graph that comparison of coefficient of the experiment and what the author has predicted. That's all.
So boiling of nanorefrigerants is to study experimental. In figure 2 of the tube, show the view of the flattened pipe with different interior height. The flattened percentage can be defined as this equation. So the result turned out in the same way with the experimental setup of the author. We can consider the effect of the flattened percentage, mass flux, mass function of the nanofluid, and the vapor quality on. The experimental condition was set in such a way to cover a wide range of flow boiling main parameters, influence of channel height, while vapor quality, mass flux, and mass function of nanoparticle on H are shown in figure 4 and 5. Within the experimental range, H had been augmented by vapor quality. This is mainly due to increased interfacial momentum on the annular liquid film with a high vapor quality and the significant increase in convection heat. Larger flattening tube improved the boiling heat transfer coefficient. So there are two major that affect the results. First, a flattening tube creates a high-shaped corner in the tube cross-section, give a strong liquid fine force on the corner, leading to the tiny liquid film over the up and down of the dust, which reduce the heat resistance and expand the H. A second mechanism for enhancing heat transfer in the flat tube is to reduce the cross-section at the constant surface area around the tube, in turn increase the fluid velocity, resulting in enhanced convective heat transfer. Increasing the mass flux will increase the block momentum and the Renoir number, resulting in the promote convective flow similar to the single phase flow analysis. Within the range percentage experimental, increasing nanoparticle percentage lead to the higher H.
And what have we known so far about improving heat transfer rate in boiling heat transfer technology? So far, we know that So far, we know that Ravichi and all explaining a paper that nanofluid is an interesting technique to promote a more feature of working fluid. For instance, adding alumina nanoparticles to intense boiling heat transfer was reported by Van and Ting. And Shekholeshrami et al. Also performed their own experiment using nanomaterial to improve the condensation heat transfer. Another one, Hao and et al. Also suggest the utilization of nanotechnology for improving boiling heat transfer rate with maximum enhancement, a ratio of up to 29.7%. Another one was by Carroll et al. They by using second law of thermodynamics for analyzing nanofluid behavior in a heat exchanger. They report that adding nanomaterial can reduce the exergy loss about 24%. Another one about the boiling heat transfer technology is by improving heat transfer rate by adding the mixture of nanoparticle and lubricant oil to pure refrigerants were conducted by Dazi et al. And flattened tube, this is another technology, has been proved to be able to improve condensations by Kim et al. Using or refrigerant 410A as pure refrigerant. And another people here, another group of scientists, does it all again, using all 600A as the working fluid. They show that more flatten the pipe, the more condensation heat transfer occur. And many experiments also have been conducted in recent decades to study nanofluid using either experimental, theoretical, or nanoscale simulation approach. So what are the limitations of our experiment here? First, we found that nanoparticle as mentioned in the paper could stay homogeneous and stable in a nano refrigerant up to only 12 hours before sedimentation occurs and makes nano refrigerant stable. Water is still an appropriate refrigerant, and another one that we found that water is still an appropriate refrigerant for most large power plants, for they usually use a large amount of refrigerant to operate, as shown in the next slide. As you can see here, since in major power plant, they usually require a large amount of working fluid to operate it. So mostly they build near the water sources, like in these two diagram, as you can see here. In nuclear power plant, they mentioned that intake from lake or river because they need a large amount of water to operate. And this one as well, the coal power plant one, they also mention about the large amount of water taken from the river as well. Therefore, working fluid usually is required in large amount for major power plant to operate. Therefore, if we use refrigerant 600A as shown in the experiment, it will be too expensive for those power plants to use. Therefore, it is still our limitations that we could not replace water in major power plants as a working fluid. Therefore, for future experiment, or if we want to implement this experiment in the real life, we have two suggestions. First, we should make nanofluid stay first. We should make nanofluid stay stable for a longer period, at least 1 or 2 months, by applying better homogenizing techniques, or use other particles that could stay homogeneous and stable in our refrigerant longer. And another one which is important especially for power generation is we should perform another experiment of nanotechnology with water to make sure it could be applied with a major power plant such as in nuclear power plant and coal power plant. So this is our conclusion for the experiments. First, we found that Flayton percentage, vapor quality, mass fractions, and mass flux are the important factors that play substantial impacts on boiling heat transfer rates. However, in practice, vapor quality is hard to control or could be too expensive to control, making it not a right choice to prioritize. Also, mass fraction is not recommended since nanoparticle could stay stable without sedimentation for only 12 hours. Therefore, we recommend that Flayton percentage and mass flux are the best option to prioritize, since they are simple and cheap to manipulate, and therefore making a good choice to prioritize when considering improving boiling heat transfer using the technique above. So that's it for our presentation. Thank you. Thank you for your attention, and if you have any questions, please kindly comment below in the comment section. Thank you.